Okay, so as you can see, the actual title of this presentation is more like the path to build cloud-agnostic MLOps platform, but here you can see it's with all of the marketing sparkles over it. And today, due to unforeseen circumstances, I will be conducting this presentation on my own. However, I would like to really thank you, Michał and Mark, my colleagues from GetInData, for helping me to put up the slides. And I'm Marcin Zabłocki, MLOps architect at GetInData, and the MLA letters here stands for Metallica. And okay, so let's play a game today. The game will be to unlock your data science teams by providing them with a cloud-agnostic MLOps platform. And today, this is the agenda for today's presentation. As you can see, we'll start with the experimentation path, then we will follow the training path, then we will go into the valley of serving, and then we'll finally conduct our presentation with the full MLOps platform. So without further ado, let's get started. So on our path, we encounter some data scientists, and they have some issues. So we would like, as MLOps engineers, to help them. And what do we hear from our data scientists? So usually, there are a few things that they are interested in the experimentation phase. So they first of all want to create reproducible training pipelines. They want to be able to switch, for example, from local to remote data sets. They want to make the pipelines reliable, and they want to quickly as possible, get some environment ready for them to work on larger projects or larger models. So how does this transition to some actual requirements? So in general, the ML project idea would need to quickly start ML project. We'll have to get some compute power. We'll need some larger machines, probably with GPUs. And the time to set up is also something crucial here. So how do we solve that? So in the experimentation phase, we like to call this solution the data science workbench. We provide it as a form of Docker container that consists of a few tools, mainly Jupyter notebooks and Jupyter Lab instances. And in addition, our data scientist teams will also have VS Code, for example, to develop the code in the cloud, a local MLflow instance, and something that I will mention later on, this black boxes in here, which is a Kedro framework, and stay tuned for more about that. So by providing our data scientists with a data science workbench, we solve at least some of the problems during the experimentation phase. But obviously, we shorten the initial project creation time, but that's obviously not everything. So next thing we have during the experimentation phase is something called usually ML pipeline. So in order to make the project and the project results reproducible, we need to introduce the concept of ML pipeline, and within those pipelines we need to have something to make those experiments reliable, to switch between local data sets and remote ones. And when we look at the model training and ML pipelines themselves, we can look at it from two different perspectives. The first one is the perspective of usually data science teams, when the things that they are mostly focused on is the experimentation and the EDA, when they are using Jupyter or their favorite IDEs. And they are obviously consuming a lot of machine learning frameworks. Any frameworks is available here, so either Scikit, TensorFlow, PyTorch, XGBoost, and whatever. But there's another perspective to this ML model training. This is our perspective of MLOps and ML engineers. So we are more like from the infrastructure side. So we have some access to the data on any cloud or any data provider. And we have some execution environment that on our side can provide our data scientists with the compute power they need, for example, to train the models or spin up a lot of training jobs at once. But as you can see here, there is something missing, and it's our job as MLOps engineers to fill up this gap. And what can we do here? And our answer for that is something we like to call MLOps framework in this layered view. And for that we use Kedro with some plugins that stitch together the perspective of data scientists, where they are focused on the top level layers, where they are using still the tools they like with Kedro. And from the MLOps perspective, we are using the bottom layers with all of the cloud tools, cloud APIs, and so on, where we are the most productive. And the biggest question is, what is Kedro and why Kedro? The short answer is that Kedro is a framework written purely in Python, and it combines the best practices from the software engineering perspectives and puts them in the data science project. So Kedro itself fits in a place where you want to have your well-established structure in your ML project. You want to have clear understanding what happens where. And the main focus of Kedro is allow you to create maintainable machine learning pipelines code, basically. And Kedro itself was created by a company called Quantum Black, which was acquired by McKinsey. And just last year, Kedro itself was donated to Linux Foundation, and it has already above 8,000 stars on YouTube, so the community is growing really quickly. And now it's time to answer why Kedro, because now you know what Kedro is, but now why Kedro? So first and foremost, this is one of the most important pieces, is the project templates and in general project structure. So imagine as, for example, if you are implementing web application in Java or Python. In Java, you would have probably used Spring, and in, for example, Python, you would use Django, and those frameworks are called frameworks because they are bringing you with some good methodology that is battle-tested, that allows you to deliver your projects faster. And the same is with Kedro, but it is for machine learning. So in Kedro, you have a well-defined project structure. Well, in all of Kedro projects, the data will be in the same place, the configuration will be in the same place, it will be known upfront where to look for it. The pipelines will be defined in the same place. So if you start using Kedro and understand this framework, every new project that you start, or even if you join a company that already uses Kedro, you will get up to speed really fast, because the projects will look the same. You will get to know and onboard really quickly. Next piece of why Kedro is the extensibility and integrations. So because it's still pure Python, you can basically do anything with it, as you can imagine. So you can Dockerize it, you can run it in cloud, and so on. What else? There are also two other useful features that will come up later on. So the first one is pipeline visualization. This is a like cherry on top feature that when you are developing your ML pipeline, you can just visualize it to understand it better. You can plot it in the form of a graph. It's useful to show it to someone else if you are, for example, explaining your complex logic behind your ML project to someone. And the last killer feature is the data catalog. The data catalog in Kedro is like a configuration file of some connection strings. You define the data that you have, and thanks to the split between the code that actually executes some logic, like training the models, processing the data, extracting features, and so on, Kedro detaches this logic, the logic of data loading from the code. Thanks to that, your code still is clear, and the framework itself, thanks to the data catalog, loads the data for you. So you can imagine that you can have data stored locally, and if you run your project with the data stored locally with the catalog pointing to your local data, it will run on your local machine just fine. And when you switch to something else, like running in the cloud, that I will show later on, you are able to do this without any code change at all. And believe me, it is really no changes in the code. So we have covered the part about the pipelines, datasets, and maintainable ML code by using Kedro. And now we finish building our experimentation phase, but this is only one small portion of some bigger solution. So you can see in here, there are some arrows that are not connected yet. So let's continue our game. We finished the experimentation. Now let's go to the training path. Now we already implemented our ML pipeline, but we only have run it locally and in some isolated manner. We want to now take it on larger data set and run it on any cloud that you like. So what problems lie ahead? So first of all, switching to bigger data. What if I need some distributed computing? Some models like neural networks need some access to compute power. And moreover, when I now try to train my model again, I would need to track my models. I would need to track my experiments to prevent going in circles, to guide my research in the right direction. And obviously, I would like to have everything automated. So to translate it to some hard requirements, we need to have some automation around the model training. We would like to push the training to the cloud and offload the actual configuration somehow from the users. But also, next set of requirements is also related to experiment on larger data sets. And how do we handle that? So let's welcome Kedro again in our training path here. And this is a map that shows you where does Kedro fit exactly in the whole world in the whole team of both data scientists, machine learning engineers, and MLOps. It gives them a common language, a common ground that they can communicate on while still being productive in the areas of focus for them. So the data scientists are using their favorite tools, and machine learning engineers can orchestrate the training jobs in the cloud of their choice. And thanks to how it's implemented, we like to call that with Kedro you can write the ML pipelines only once and then deploy them almost everywhere. And I encourage you to check out our GitHub. There are plenty of open source plugins that you can use at your own pace. We have also some YouTube videos with video tutorials basically for you to try them on. And just yesterday, we were able to, during our workshops here at this conference, we conducted a successful workshop and we live demoed the same project written in Kedro, and during our workshops we've deployed it in SageMaker using native SageMaker functionality, in the center on Azure ML, and the last one is in Vertex AI. So that was the project with the same code base, with the same Python code, with the only change being the configuration. And if you really like to see this live, reach out to us. Okay, so by leveraging cloud, we provide our model training with some infrastructure, with some code repository, automated training. Everything is containerized in Docker in order to run this stuff in the cloud. And we, as needed, since we are using either, for example, Vertex AI or SageMaker or Azure ML, those services allow easy access to GPU and distributed computing. We can leverage that. And the next section is about the data catalog. So again, when we transition to the cloud, thanks to the feature of data catalog that I've mentioned before, in Kedro, we can easily scale up to the cloud and use remote large data sets instead of the ones that, for example, you started with locally. But that's not it in the training path. There's something else that I've mentioned. So you cannot deliver a successful MR project without you tracking the metrics during training and guiding your research in the right direction. So for that, we need to not only trace the metrics, but also save the models to be able to understand what happened in the previous runs and be able to select the best model that we came up with so far. And for that, we introduce model registry. We usually choose MLflow because it's fully cloud agnostic. You can deploy it anywhere you like, as long as it can run containers, for example. We always deploy it in a secure manner, so you have some authentication layer on top of it. And this diagram shows the whole training, simplified version of the whole training pipeline. So we have the code repository of our Kedro pipeline. We have CI/CD pipeline to Dockerize it, and we are using cloud to run the pipeline with Kedro. But the experiments and the trained models are stored in the MLflow. So that covers the model registry part. And we add additional piece to our whole MLOps platform. The next one, the previous one was experimentation. Now we have training, but yet there are still some unconnected arrows here. So let's continue our path to the next stage. And the next stage is serving. So now in this world, we have already great cloud-based training infrastructure. We were able to train hundreds of models, store them securely in model registry. We know what metrics they produce, but they're still lying there in this repository of nothing, and they are not bringing nothing to the business because they are not deployed yet. So we need to deploy them somehow. And again, there are some challenges on the road. Besides the deployment itself, we want the deployment not only be possible, but also be auditable. We want to sometimes scale up models to serve more predictions. And also, we would like to be able to understand how the model behaves after it is deployed. So to once again translate it to some hard requirements, we want to serve some predictions. We want to integrate the predictions with existing applications, and also we would like to have those deployments auditable because we want to follow the best software engineering practices. And for that, what we do in our cloud agnostic MLOps platform, we've introduced a tool called Model Deployer, which is again cloud agnostic. So from the perspective of the deployment, we have some configuration in Git repository. It triggers automated training job, and then the model deployer does the rest for you. So remember, our models were stored in the model registry. So our model deployer, based on this configuration, can take this model from the registry and deploy it to the cloud of choice. So whether you are running on Vertex, on Azure ML, on SageMaker, does not matter for the deployer. We can deploy anywhere. But what's also important that besides that this part was versioned in the source control repository, the model registry also will reflect what's deployed in production. So for example, in here we deployed model version 2 in production. So after the successful deployment by the deployer, the state will be traced there. Okay, so now we applied GitOps, CI/CD to deploy the models. We can deploy them either online or to batch services in the cloud to obtain the predictions. And we have auditability of those models in production. But is that everything? So if we play this game further, there's one more nasty thing that you can encounter there, and our model can unfortunately step into this nasty little field, and it's called data drift. So after you deploy your model, two nasty things can happen. One is that directly after the deployment, the model can immediately serve much worse predictions than it was during training, but also it does not have to happen immediately. It can happen also after some time. So how do we handle those? And for that, we introduce a component called model monitoring. So far, we've been using Evidently, and the general principle is that instead of the applications accessing the model serving directly, we expose our models through this monitoring proxy, which underneath the hood actually proxies the request from our application directly to the model, sends it a response, but the request and the response is sent by this proxy to some queue in the cloud or in the Kubernetes, the one that the cloud provider actually has, so we can leverage that. And this sampled traffic, because it's usually not 100% traffic, is sent to Evidently, and we have two options there. The first option is to real-time monitor it in Grafana. So some metrics can be traced in Grafana, and we can build alerts on top of that, and also some triggers to, for example, push some information to the training jobs to retrain our model on newer data. But it can also work offline in the form of batch predictions. So you can, for example, daily on a weekly basis, run some batch job to compare the data that was collected during this traffic sampling against some existing data set that you have trained, and you will be able to compare the profiles of the data, and you will see, for example, that some features drifted from what they originated. Okay, so that concludes the model monitoring part. We have our last component, which is serving, and we can attach it to our whole MLOps platform. So now we arrived at our last path, which is the whole MLOps platform that is cloud agnostic. And the picture that we've built so far today looks like this. It has all of those components that I just described. Experimentation, training, and serving. But you can imagine that the picture is not as simple as it looks like here. It looks more like this. So the way we approach the process of building the whole cloud agnostic MLOps platform is that instead of building huge block specific to one cloud, we pick and select the technologies that are easy to interconnect with each other. And thanks to that, you can, as a consumer of this platform, you can pick and choose the technology you already, for example, have, or the one that suits the best your needs, and we'll be able to connect everything together and provide you with working MLOps platform. To sum this up, we already successfully integrated our MLOps platform, and one of the examples is Willa. It was GCP based, and not only it was related to MLOps platform, but also data platform. So everything was automated with Terraform. There was also, from the data engineering perspective, the DBT here, and the whole MLOps part was built around Vertex AI, Kedro, and MLflow. And there are there is one pending project in progress, the one already done. So the same platform with the same infrastructure is being deployed in AWS with Airflow as an orchestrator for Kedro jobs. And the last one is also one that I'm particularly proud of, is because thanks to all of the automation, so all of the diagram that you saw before for the MLOps platform, it was all integrated within the Terraforms, and we were able to deploy the whole platform from scratch in less than 1 week. So it is indeed possible to do this fast. And it's like 2, 1, 0. It's 5 minutes for you. Thank you very much.